Welcome back, and we're moving on talking about electrostatics, and I want to continue talking about the basic things around charge as I started with the grade 10 work. One thing about electrostatics is that whatever you learn at grade 10 stretches up until grade 12, so you need to know all these basics. I'm going to go back there. Now here, conservation of charge. When charged objects come into contact with each other, the charge is spread evenly on all of them, okay? And the object will have equal magnitude of charge after they have been separated. But before then, okay, we also need to know that charge cannot be created or destroyed, but can only be transferred from one object to another. This is the principle of conservation of charge. And when is it transferred? It is transferred during friction, where electrons would move from one object to another. But to show that charge is being conserved here, we would see that the number of electrons gained by one object will always be equal to the number of electrons lost by another, okay, or by the other object involved in that friction. Okay, now we're talking about like charges repelling each other and unlike charges attracting each other, and therefore the question or the issue of force comes in, because we can't talk repulsion and attraction and then we're not talking force. This is force we're talking about. Now, this brings us to something called Coulomb's law. The electrostatic force between 2-point charges, or between any two charges, whether they are point charges or not, is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Now that is summed up by this mathematical relationship here, which is a mathematical expression of what Coulomb's law is, that the force that exists between any two charges is given by K Q1 Q2 over R squared, where K is a constant, okay, with a value of 9 by 10 to the power 9. Okay, that's what you have there. I don't want to worry much about the units now because I don't have the time. Now here is an example here that I want to use to explain further on that law there. Two charges are 0.3 meters apart. Find the electrostatic force between them if the charges on them are -8 microcoulombs and +3 microcoulombs respectively. Now all we need to do here is to use Coulomb's law to solve this problem here. Now you would see that your charge is given in microcoulombs, so you should be able to move from micro to coulombs, microcoulombs to coulombs. What do? From micro you multiply it by 10 to the power -6. If they said nanocoulombs, because sometimes they use that, by nanocoulombs, moving from nanocoulombs to coulombs, you multiply by 10 to the power -9. Then you are in coulombs. So what we're going to do here is to say 9 by 10 to the power 9, which is the value for K. Q1 is what? It's -8 by 10 to the power -6, because it's micro, times, what's the other one? It's +3 by 10 to the power -6, so that we're talking coulombs, divided by R squared. What is R? The R is the distance between them, so it's going to be 0.3 all squared. Then you work that out. Okay, now let's see how what that works out to be. Hope I will have time for this. So 9 to exponent 9 by 10 to the power 9 times 8 by 10 to the power -6 times 3 by 10 to the power -6. What is that? Okay, that is 0.216, which is therefore 2,16 by 10 to the power -1 divided by 0.3 times 0.3. What is the answer there? You've got that as 0,09, and therefore that will be 9 by 10 to the power -2. You work that out, okay? So it's going to be 2.16 to exponent -1 divided by 9 by 10 to the power minus 2. Okay, and what is that? And then we find the force here to be 2,4 newtons. Okay, so that is how you use Coulomb's law to solve electrostatic problems related to charges, the force that exists between any two charges. Okay, now electric fields. An electric field strength, I'll zoom straight there, is the force experienced by a unit positive test charge at a point. And we make use of E equals F over Q to find the electric field strength. Okay, right. Now, this would mean that any charge would create a field around itself. And the force will be the electrostatic force between the mother charge and the positive test charge. I'm talking about the mother charge here because here you would see we're using that test charge there. Okay, now field patterns. If I've got a negatively charged, this is a negatively charged field, object, the field will be coming into, so hence the direction there is into. But you need to make sure that these field lines are at right angle to the surface. If it is positive, it's radiating outwards, that's the direction. Again, make sure that they land or they move out at right angles. See you in the next section.